by Agostino Migliore. This is from the theoretical Department of Chemistry, from the group of Avram Nitzan. And the subject of this talk is theoretical modeling of negative differential resistance in molecular junctions.
Okay, so, no, it is, okay. No, I understand that you started from, okay. So, I will talk to you about the theoretical modeling of a negative differential resistance, or in short, NDR in molecular junctions. That is the fact that in suitable voltage ranges, the current can decrease while increasing the voltage, and so you can observe peaks in the current that are called NDR peaks. In short, I will give a motivation for this kind of studies. I will shortly describe the theoretical approach that we use in studying this kind of phenomena, and then I will present some of the results that we got theoretically, and also confront them with some experimental results. The motivation is the increasing evidence, experimental evidence of NDR phenomena, which often, like in this experiment from Science in 1999, appear like peaks in the current because at a suitably large voltage the current will rise, and then there is a region of negative differential resistance where the current decreases sharply with the increasing voltage, and so you have this peak with which is very sharp along the voltage scale, and which can have very high peak to valley ratios, and thus can be exploited in many applications in nanoelectronics, like for example switches or high frequency oscillators, and this kind of a phenomenon need still for a lot of theoretical study, because until some years ago it was thought that this kind of strongly nonlinear charge transport phenomenon could arise only from strong couplings between electrodes and the bridging system, for example a molecule, while many recent experiments showed that it can occur in systems where the bridge is weakly coupled to both the electrodes. And then, since recently were developed many junctions where the bridge is represented by a molecule, it is very important and interesting to relate this phenomenon to physical parameters like the reorganization energy, about which I will discuss, and the temperature. Previous theory was able to grasp some features of NDR, but still not able to understand, for example, why after NDR peak you have again an increase in the current, or for example how the reorganization energy can affect the NDR or the temperature. And so our starting point was just this model, this previous model, that we integrated with other concepts. According to this model, you have a molecule which is modeled by means of a few states. For example, here A is the ground state of the molecule with n electrons. For example, the neutral molecule. And at a certain bias, you can have an electron transition from the left electrode to the molecule, and the electron will localize in the molecule, for example, as described by this molecular orbital distribution, and the molecule will switch to state B. And this can happen with a rate which I will call RAB. Obviously, this switch requires to fill this energy gap epsilon1 between the two states. And this can occur with a significant probability per unit time only when the bias is high enough. And so the electrode can provide electrons with a suitable energy. And after this, the electron can be delivered to the right electrode and switch back to state A with a rate that is RBA. At the higher biases, you can enable a different transport channel which involves this state A and another state, a different state with n+1 electrons, where the excess charge is localized differently in the molecular system. And this state will be a trapping state if the rate for the inverse process by which the electron is delivered to the right electrode is very slow, which means that most of the time the excess charge will be localized on the molecular system and will not be transferred, so you do not have a conduction. So the overall current will be slowed down by the population of this state. And according to this model, you have NDR if the coupling to the right electrode of state C is small enough that this inequality is satisfied, where these two are the couplings of the molecule to the two electrodes when the system is in this transport channel. So these two transport channels, the one that involves a switch between states A and B, and the other one which involves a switch of the molecular system between state A and C, are alternative ones. So the current can exploit this transport channel or the other one. And since we have a system which is weakly coupled to both the electrodes, we can describe the charge transport as a combination of a sequential electron transfer steps from one electrode to the molecule and from the molecule to the other electrode using classical type master equations. The other ingredient that we added to this theory to make up our theoretical approach is the Marcus theory for electron transfer, according to which the electron transfer between two redox sites or between a molecular redox site and an electrode requires the support from the nuclear reorganization. For example, in this energy landscape, if we have a molecule and a metal, this can represent, this potential energy surface can represent the molecule in state A and this the molecule in state B. When the bias is high enough, one electron with the energy E can be provided to the molecule so that it can switch to this state, and then the system can switch to state B, and thanks to the nuclear reorganization, the system can reach the bottom of this potential energy surface, and again in energy is the reorganization energy, which is so a very important parameter in characterizing the electron transfer process, and so the current which arises from this electron transfer process. And this has been demonstrated experimentally. For example, in this very recent paper, they measure the current as a function of the gate voltage, and you can see that there is a peak in the current because when you change the gate voltage, you are changing the relative position of the molecular levels which are involved in the transport, and Fermi levels in the two electrodes. So when you are applying a gate voltage, you are essentially making in such a way that at a certain gate voltage, the molecular levels are within the Fermi window of the two electrodes, and you have the maximum of conduction. And then you increase again the gate voltage, and at a certain point, the molecular levels will go out of the Fermi window, and the current decrease again. And they show how there is a strict correlation between the reorganization energy and the current peak, because what they do is that they are changing in their experiment the initial set point current, which is a way to change the distance between the tip and the sample in their setup, in their STM setup, and this changes also the reorganization energy. And they are measuring at each separation both the current peak and the reorganization energy, and as you can see, the two behaviors are strictly correlated. According to Marcos' theory, the electron transfer rate, if the electron transfer is occurring between the two redox molecular sites, is given by this expression where the reorganization energy lambda appears in an exponential factor. So it is a crucial parameter in determining this rate. When you are considering an electron transfer process between a metal and a molecule, you need to insert this expression in an integral where you have also the Fermi distribution for the metal. And these integrals are of utmost importance in electrochemical reactions involving a metal electrode and a molecule, and we solved them analytically. And this was very important for us because our analytical solutions allowed us to obtain all the results that I will show you. I mean, I will skip the analytical solution, but I will show you the results. It is not interesting by itself. A very important parameter in understanding the competition between the two transport channels in determining the current through the junction is the tunneling energy gap. It means that you need to overcome a certain energy gap before enabling the current through a given channel, which involves the switch of the molecular system between two states. For example, if we consider the AB channel and the left electrode and the molecule, when we have this threshold value for the potential of the left electrode relative to the molecule in order to enable the AB channel, or better, in order to enable one of the electron transfer process involved in the AB channel, where μL is the chemical potential of the left electrode. And analogously, we obtain the threshold potential for the right electrode. The current through a given transport channel is enabled when both of these tunneling energy gaps are overcome. And from our theory, we derive this expression for deciding if the access of the two transport channels along a bias sweep is sequential or not. If you do not consider the reorganization energy, you can say that whenever you have different values for epsilon 1 and epsilon 2, that is the difference in energy between states A and B or A and C, then you have a sequential access of the two transport channels. When you introduce the reorganization energy, it is not always the case, and it will depend also on the temperature if you have a sequential access of the two transport channels. And this will modify the dynamics of the current as a function of the voltage. And in particular, from our theory, it comes out that an important parameter to take into account is the ratio between these two rates. That is, the rate to occupy state C and the rate for the inverse process, for the reverse process where you empty state C. If this ratio is high, it means that it is the process to empty state C is very slow compared to the probability per unit time to occupy state C. So C is acting as a trapping state. And the important element is where the voltage range where this occurs is located relative to the threshold voltage to enable the other transport channel. And not only the coupling strength to the contacts as predicted by a previous model. So now I will show some results and some applications of this theory. For example, here, the condition established by Murali-Dharan and Datta in the paper I showed before for the occurrence of NADR is satisfied. So we would expect NADR, but we do not observe any NADR because the condition for a sequential access of the two transport channels is not satisfied. There is a notable overlap between the voltage ranges in which the access of the two transport channels occurs. And so you can see only directly an increase of the current to the final plateau value, which you have at high voltages if no other electronic states are involved in the charge transport in the energy window that you are exploring. Here it is another case where, according to the previous model, you should have NADR, and which you should have a sequential access of the two transport channels. But what happens is that for this transport channel, the reorganization energy is much higher than for this transport channel. And so the effective tunneling energy gap of this channel is higher than for this channel. So what happens is that the slow channel is accessed first, and then the current rises at the final plateau value at high enough voltages. And so you do not observe NADR. Here you can see how the occurrence of NADR can depend on the temperature. At this temperature, you do not have a well-separated voltage ranges for the access of the two transport channels. And so you do not see any NADR. While at decreasing the temperature, you can see NADR peak, and the height of this peak will increase while reducing the temperature. In particular, we find that decreasing the temperature, the height of the NADR peak will increase, and the peak will shift towards higher voltages. And both of these features were observed in experiments. For example, in this one. Okay, I don't need it. Then, here it is a case where, according to this condition in the Murali-Dharan data model, you should have NADR. And here you have also a sequential access of the two transport channel. So according to the previous theory, there is no reason not to observe NADR. Instead, we have a reason according to our theory. And the reason is that this ratio is high at voltages where the current through the AB transport channel is still not enabled, which means that the blocking state is active before voltages where the other effective transport channel can be enabled. So you cannot see a rise of the current through the AB channel and then a decrease of the current when state C is populated. In this case, the current can rise significantly only when both of the transport channels can be accessed, and so it will go directly to its final plateau value, which arises from the competition of both the transport channels. So in this case, this condition is demonstrated not to be sufficient for the occurrence of NADR. This is another situation where all the states involved in the charge transport are coupled in the same way in all the states involved in the charge transport, the molecular system is coupled in the same way to the electrodes. In fact, as you can see, IAB is the current that you would have in the absence of state C. And the IAC is the current that you would obtain in the absence of state B. And they are the same at a high enough voltage. I mean, in this event, C is not a blocking state because of a small coupling to one of the electrodes. Nevertheless, and so this condition is clearly not satisfied. Nevertheless, we can observe NADR. And this is due to the fact that, again, here you have that initially you have a transport through the AB's channel because the corresponding tunneling energy gap is smaller. Then, at a certain point, you can occupy state C, but the reverse process to empty state C is still not enabled. It is very slow, so that both the process to deliver this electron to the back to the left electrode or the one to deliver it to the right electrode are very slow, and you have a decrease in the current, and so you observe NADR. And then, at a high enough bias voltage, the current can rise to the final value, which is not 2 times this value because these are alternative transport channels. So the current is not just the sum of these 2 currents. And you can see, for example, the similarity of this curve with this experimental current voltage characteristics. And you can see that also in this experiment here you have just a plateau, because in the explored voltage range you do not have any other electronic state involved in the charge transport. Although here we use the value of the reorganization energy for which all these dynamics occur in a larger voltage range. And in this case, this condition is not necessary for the occurrence of NADR because we observe it, although this condition is not satisfied. And finally, I wanted to draw your attention on this slide where we show how the current can be controlled by changing the reorganization energy and the temperature. I described already this kind of behavior which is observed in many experiments. But there are also many other experiments where the trend of the NADR peak with the decreasing or increasing the temperature is the opposite one. For example, in this case, you have an increase in the NADR peak when the temperature is increased, although the peak to valley ratio is decreasing. And the reason for this is that when you increase the temperature, you are smoothing the dynamics of the current as a function of the voltage. And so what happens is that this transport channel, the transport channel which is enabled at this voltage, can give a larger contribution at this voltage to the current at higher temperatures, and so the peak intensity will increase, while here it was decreasing with the temperature. Finally, if you increase the reorganization energy for one channel while keeping fixed the one for the other channel, you can see that finally the NADR disappears. And so this provides a way to control the behavior of the NADR effect and of its dependence on temperature, changing the reorganization energy, which means changing the solvent or changing which part of the solvent is more active in affecting the behavior of the system. So finally, my conclusions are that we propose useful, at least we think is this useful, analytical framework for the investigation of electrochemical reactions at metal electrodes. And our current expressions, include the effects of the nuclear relaxation on the energetics of the electron transfer process involved in the transport through the molecular junction. We can grasp effects of the reorganization energy on the current, and specifically on the NADR, although in our work we explored also other nonlinear charge transport phenomena. And we can explain various scenarios in which NADR can occur or not, and all of them were observed experimentally. For example, also the dependence of NADR on the fact that you have a molecular bridge which has asymmetric contacts with the two electrodes. And we can describe current voltage characteristics where the NADR peak is followed by a current increase, as it is in various experiments. And finally, we can give a theoretical description, justification of the dependence of NADR on the temperature and the reorganization energy. And finally, I'd like to thank Professor Avram Nitzan, with whom I am collaborating, and Philip Schiff from his research group, Professor Spiros Skortis from University of Cyprus, and finally, I wish to thank you for your attention.